Hello and welcome to today's webinar, Machine Frames Made Easy.
Before we begin, let me ask you a question. What are your challenges with frame design? Is your current system just a tedious process with all the manual corner definition? Are you having problems with shop floor errors where machine parts are running into each other when you fire your machines up? Are you over-designing because of the cost of analysis? Are you skipping the welding documentation process because the cost of applying beads is just too time-consuming? Or is it too time-consuming packaging up all the engineering documentation? Things like 2D drawings, viewing data, parts list, shop floor instructions? Well, we think we have a better way. Let's get started. Hi, my name is Chris Kasperzak, and I'm a 25-year veteran with Siemens. Just like you, I have an engineering background. Years ago, I switched from engineering into software development with the goals to make engineering software more productive and easier to use. Currently, I'm a product manager, and my job role is to turn vision into reality. With me is Scott. Scott?
Thanks, Chris. And my name is Scott Felber. I've been with Siemens over 30 years now, focused primarily on NX. Today, I work in the product marketing organization for NX. Before that, I held a long-time role in NX technical pre-sales. I have a degree in industrial engineering from the University of Wisconsin-Milwaukee and a master's of engineering management from Marquette University, also located in Milwaukee, Wisconsin. Today, we will go from concept through documentation with a complete frame design. We will design the frame, then we will animate the frame to test for collisions, we will test it to ensure structural integrity, then we will weld it together, and finally we will send all that documentation out to the shop floor for manufacturing. Our first task for today is design it. What are some of the challenges with that? The challenges with traditional CAD system is it's a very labor-intensive process to be able to draw the underlying cage from which to design the frame. In addition to that, many of today's CAD packages tend to have standardized features, but they won't give you the proper solution without a ton of manual intervention. And finally, it's the total lack of inadequate libraries found in many of today's existing CAD systems. We aim to make that a better solution.
Scott, great summary. I'll bet a lot of you are struggling with those same problems. NX Structure Designer was designed to alleviate a lot of those issues. It's intended for welded frames that are made from standard stock. We have a great 3-click cage command, rules-based member placement and corner definition so you get the right answer out of the box. We have an extensive library filled with different shapes, sizes, and materials. You can also turn a visual reporting option on to see exactly what stock makes up your frame. Let's have a look. We have the start of our machine with the key components in the correct location. Now it's time to create a frame to maintain those positions. Creating the initial cage is as simple as 3 clicks. Adding interior elements can be done by copying or moving existing elements. We'll copy the base elements to meet the machine's transport frame. Snapping to existing geometry will guarantee fit and position later when we create 3D members. We'll move these elements into position by using the mounting tabs as a guide. We'll repeat the process on the opposite side. Lastly, we'll add a footrest that will also stiffen the vertical legs. An element move will complete this process. During any move or copy, you can snap to existing geometry or enter a desired distance. You can also use sketch commands to create the cage. Now that the cage is complete, let's add 3D members. Structure Designer includes an extensive library consisting of industry standard shapes such as angles, channels, beams, rectangle, and square tubing. There are different materials, standards, and grades. We'll select square tubing and click the desired cage element. Structure Designer is rules-based so you can specify the initial connection type and member orientation. Notice miters are added to the top and butt connections to the interior. Should you want to override the initial configuration, pick a corner and change it. Corner types range from none, smart extend, miter, butt, cope, and match cope. Here, we'll change 2 connections to smart extend, leaving an open end. We'll cap this off later. All members and corners are fully associative to the cage, so if you change its size, the 3D model will update accordingly. Since the bulk of the machine rests on the midsection, we'll use a thicker member for these 4 components. Our initial rules were to place members at their center point, but we need to move these members down to meet the base of the mounting tabs. A handy option lets us reposition the member using a grid of selectable points. The selected point will align to the selected sketch element. Butt joints are automatically applied during the change. As we add the final members, we'll need to offset them in two directions, down and to the inside. The alternate origin grid has selection points in each of the four corners, and by selecting the top corner, the member will snap to align with the sketch element. It's important to note that the change to one member will be applied to all members in the creation step. Again, the butt joint will be created automatically. The footrest does not need to be as rigid as the midsection, so we'll use a low-cost angle shape. Upon selection of the sketch elements, notice the orientation control that can be used to override the initial orientation. The member can be flipped X or Y, rotated, and even offset from its sketch element. You can also trim the member back to account for the welding process. As we select members in the navigator, notice how they are packed if they are geometrically identical. Should a packed member be modified with the addition of, say, a mounting hole, it will be automatically removed from the collection. A similar packing process can be used to consolidate members to create drawing cut lists. The last few steps will be to add specialty features. First is to cap off the open-ended members. Here, we'll use an exterior cap while preserving the overall length. Gussets will be added to stiffen the top corners. Simply pick member faces and a gusset will be added. The gusset position can be interior or lapped, and the shape can be triangular, triangular with nose, square, or rectangle. Dimensions can be adjusted to control the size, thickness, and location. As we add the remaining gusset, notice the ease of use. Select the face, click Apply, and repeat. All dimensions are preserved so you can speed through the design process with minimal effort. Gussets can be consolidated in the parts list, simplifying the ordering and manufacturing process. To simplify transport of this machine to its final destination, we'll add some hoist tabs. Adding them is a similar process like gussets. Choose the shape, enter the size, and select the location. The tab shape can be triangular, rectangular, semicircle, or trapezoidal. We'll add a total of 4 to the top rails. As expected, similar tabs can be consolidated into a single parts list entry, but with the correct quantity. This consolidation process helps ensure the correct quantity are ordered or manufactured. The combination of creation rules to automatically set the initial placement option greatly speeds design, and the extensive library gets designers creating faster. Last but not least is adding mounting feet. We'll add square pads to the bottom of each leg that are complete with mounting holes and corner chamfers. Entered sizes are retained in the dialog, so adding them is merely dragging the desired shape to near the member end. Location selection is fairly forgiving. Just pick any geometry near the end and Structure Designer will take care of the rest. For a quick view of what members are used in this frame, an option can be set to show similar stock in the same color. This provides a fast visual inspection to help ensure no incorrect sizes were used. Our machine is now complete.
That was an awesome demonstration of the ability to be able to quickly design a machine frame very easily around existing components. It was super easy to develop the cage and then be able to get all the members from the library quickly in there. Also, the rules-based corner structures was an awesome addition to be able to quickly get the layup we needed for all of our corners. I really believe using a system like this, you can save over 60% of your time on a frame design in the cost alone based on time. Step 2, animate it. How can I ensure that my moving parts do not collide before I build my machine? What are some of the challenges today around animation and finding these collisions? One of the biggest is just the assembly structure that's used to design your parts does not easily convert itself into being able to do motion studies. Also, it's very hard sometimes to be able to define the motors and the motion you need, all while being able to find out if you have collisions. Let's see how machine frame design made easy can address some of these issues.
Scott, you hit the nail on the head. I think a lot of people don't design assemblies with motion in mind. NX Animation Designer is a motion application for doing kinematic studies. You can create realistic simulations with standard motors and joints. We have a timeline control so you can get the exact sequence of operations. And with built-in collision detection, you can find interferences between moving parts. But my favorite part is you're free from the assembly structure so you can move whatever you want, wherever you want. Let's take a look. Finding interferences between moving parts first requires the correct sequence of operations. Animation Designer is a perfect application for this task. Here, we want the gripper to traverse across the table, pick up a part, and return. We'll look for any interferences along the way. A common challenge here is the assembly structure. There is no guarantee that motion was considered during the design process. As we highlight various subassemblies, notice the linear bearing is a member of a fixed base but needs to slide with the transport frame. Rigid groups let you define what can move and were based on the subassemblies. The fix is simple. Move the linear bearing from the fixed rigid group shown in orange to the cyan-colored rigid group that will move. Joints define how rigid groups can move, whether it be along or around a vector or around a point. We already have the joints created, and a handy move command lets us validate the basic articulation. Now it's just a matter of adding a motor to each joint with the correct runtime to drive the gripper to the correct destination. This task is simple with inverse kinematics. Just indicate the start position and destination. You can add interim points along the way to generate a complex path, but for this machine, moving from point A to point B in the shortest steps is the goal. Animation Designer will compute the runtime for each motor to cause the desired motion. A click of the play button validates the results. Recall the goal is to set the correct sequence of operations, but all the parts are moving at the same time. Sequence can be controlled through a timeline editor. We'll change a color option to identify which events control which motor. We'll give the machine a 1-second startup time, then the plunger is to move across first, then the gripper head rotation, and then plunge. Notice how easy this process is by simply moving the event bars. Duration can be changed by adjusting the bar's width. Adding the return is by mirroring the selected motors. Watch how the animation is computed and played in real time. Now that we're certain of the articulation, we can analyze the assembly for interferences between moving parts. Any parts highlighting in red indicates an interference. While we're not so worried about the interference near the end as we selected an arbitrary destination point, however, the plunger hitting the frame must get fixed. Since all these applications are tightly integrated, all we need to do is adjust the frame's cage. We'll drag the upper point a bit higher to allow clearance between it and the moving component. Once complete, all parts update to the new size. Members are changed while retaining specific corner, gussets, caps, and hoist points all update to their required location. This update process also checks members' geometric uniqueness. Should any of the identical grouped members become unique, they will be given their own group. Other types of edits can affect all members. A special command lets you select multiple members, even if based on a different stock, and change them to become the same. A quick replay of the animation shows the interference violation has been addressed. While this interference was obvious, imagine trying to find a more obscure interference deep inside of your model.
Thank you, Chris. That was an awesome demonstration once again. And really the value here to you, the end users, is you can reduce your physical prototype costs. So what do we think that is in savings in dollars? If you look at the chart here, we can see that with NX using Animation Designer, it's very easy and very quick to be able to do. You can save tons of money on one job just by being able to find that collision up front, being able to solve that problem and get it resolved before you even start to build your machines. Step 3, test it. How can I ensure that my frame is strong enough to stand up to the rigors for which it was built? What I need to do is I need to be able to do that in simulation. But what are some of the challenges today with simulation to be able to test these strengths? One is the significant amount of time it takes to prep beams for finite element analysis. The other one is the inability to be able to combine the beams with other non-structural elements. Let's have Chris show us how this is easy to do.
Yeah, Scott, I often hear people say steel is cheaper than brains, so just over-design it. The integration that we have between NX Structure Designer and SimCenter 3D is automatic centerline creation, transfer of those centerlines, materials, and shapes into the mesher, so you have a very streamlined way of getting your data from design into simulation. The system is all fully associative as well. So if you make a design change for improving quality, you don't need to worry about redefining your mesh or your boundary conditions. We'll take care of all the heavy lifting for you. Let me show you what I mean. Determining beam deflection is fast and easy. watch how we can leverage design data into the finite element modeling application to see if our machine frame is strong enough. A special command inside of Structure Designer automatically creates beam centerlines and associates the appropriate cross-section and material. This step greatly simplifies the meshing process. Inside the application, we'll create a new simulation model and load the beam centers that were just created. Now meshing is simple. Just rectangle select the entire model and meshing is automatically created from the centerlines and cross-section. While this model only has beams, we could have included other parts such as the top or mechanical parts. These, of course, would require a separate mesh type, but the point is you can easily simulate many different types of components. As with any FEA simulation, after meshing, it's time to add the boundary conditions. First, we'll apply a constant load to the midsection, simulating the weight of the machine. While 600 pounds is more than the total weight, this will give us a reasonable factor of safety. We'll simplify creation of the fixed restraints and simply select the lower leg sections. Because this model is made from standard stock, beam element meshing and solving will give fast, accurate answers. Solving is fast due to the beam elements, and as you saw, setting up the mesh was simple because centerlines, cross-sections, and material were leveraged from the model. The results can be displayed, and an option lets us see the results as if it were a solid. As we animate the results, notice the maximum deflection is around 0.2 of a millimeter, well within our design parameters. However, a change has been requested. It's too difficult to bolt the transport frame to the square tubing, so we've been asked to change the midsection members to channel. Let's make the change and see if the deflection is still acceptable. The process is simple. We return to the design and simply change the members. A handy command allows us to pick any member and select a new stock. For this change request, we'll use standard UPE 120 stock. We need to ensure the interior-most members can be welded to the flat side of the channel. During the swap, notice how we have full control over the orientation of the members. By visual inspection, the orientation is correct. Because of the rules, butt joints are added automatically. The last step is to update the beam preparation model, which contains beam centers, cross-sections, and materials. Now it's a matter of updating the mesh and resolving. Boundary conditions update to the new members as they were applied to the underlying beam centers. Note, adding or removing members may affect the underlying sketches and may require updating the loads and constraints, but that's an easy process. The final step is to resolve the model. Again, since our design is based on beam-type shapes, beam elements are used for the mesh, which tend to solve very quickly. Here, the entire model solves in just a few seconds. As we review and animate the results, the total deflection is slightly higher. This amount is still within our design parameters, but now the machine can be assembled easier.
Wow, Chris, that was great. And what I really think here the value is, by being able to do this simulation up front, you have more time now to do quality-driven iterations. Because you understand the problems up front and are able to address them sooner, you have more time to get to the best solution possible in a shorter amount of time. One of the things I really think this helps with is being able to get the correct size you need for the beams for the job that's going to be done and not over-engineer, which increases your cost due to the high cost of steel and other members and shipping down the road. Step 4, weld it. How can I accelerate my manufacturing process? And by manufacturing process in the context of frame design here, what I mean is the ability to weld these frames together. Really, what are some of the challenges along welding with today's traditional solutions? One is it's the time-consuming identification of where the welds go and being able to document those welds to be able to get that information out to the manufacturing floor so they can create the correct welds. Most people at the end of the day simply want the information that they need to be able to weld the structures together and not so much just model the welds. Let us take a look at how using a rule-based structural welding approach will be able to reduce your time to A, create the welds, and B, then document those welds to be able to get them out to the manufacturing floor sooner.
Yeah, Scott, I totally agree. Most people jump right to a drawing and annotate it with the weld information because the beads are just too time-consuming to put on. The integration that we have between NX Structure Designer and Structure Welding is totally automated. We define where the welds go during design and just recall and double check those in the welding application. You can create beads if you want to, but the goal is to go right to the PMI step and annotate your model. And you can use the weld information to drive a robotic process. Watch this. Creating the welds and documentation for our frame is an automated process. Since weld locations were identified during the design phase, all we need to do is review those choices and add the PMI callouts. In the structure welding application, we'll verify the types and locations of the welds. You can individually choose what welds to create, or you can select the entire frame to create all welds. After the system finds the assigned edges, structure welding uses a set of rules to determine the weld type. Depending on the geometry, a butt, T, corner, or lap joint will get assigned. Once the process is complete, a preview shows the welds in a color-coded type. Notice how butt joints are shown in red, T joints are blue, and corner joints in green. Notice how welds at each corner type were identified, as well as the welds for the hoist tabs and gusset plates. The welds look complete, so we'll finish the process. An actual weld feature is created, but not the physical weld. In a design such as this, physical beads are rarely needed. Beads can be added later. The curve for each weld is created and can be used in a robotic welding process. The advantage of creating weld features is being able to add PMI. Watch as we rectangle select all welds in the entire corner of the frame. Structure welding will add a weld callout based on the bead type. As these weld annotations are being drawn, note that these same callouts can be recalled in draft, saving you extra time. To tidy up our PMI, we'll move the callouts to a better location. A simple drag and drop lets you move them to the right spot. As we zoom in, notice the details were already filled out. Should you want to change the type of a weld, just select the weld and change it. Imagine the time to create beads and callouts one weld at a time, but with Structure Designer and Structure Welding, creating the welding documentation is just a matter of minutes. We could repeat this process on the other members, but since they're all identical, a typical note will suffice. A quick review of what was created with literally a few clicks is impressive. Notice all the weld features in the navigator along with the PMI dimensions. Now we're just about ready for production.
Wow, Chris, that's great. I think one of the key benefits here is being able to start manufacturing faster. And how can you start that manufacturing faster? Automatic creation of that product manufacturing information, or PMI, that can be sent out directly to people on the shop floor to be consumed either in a 3D method, which we'll see coming up, or in a 2D method on a traditional drawing, or even with today's automated welding systems, being able to pump that information directly into the automation robots that can then do the welding for you. This will significantly reduce the amount of time that your product spends out on the shop floor. That was an awesome demonstration, Chris. Thank you. Finally, our last step, document it. And really, when I say document, it's how can I eliminate drawings from the shop floor? And what we need here is we have a wealth of different information that sometimes isn't even on traditional drawings. We need certain things like we need cut lists and part lists and welding information and other dimensional sizes and tolerances to be able to manufacture that product. What if I could package up that documentation in an easy to digest three-dimensional form? How much time would that save me, and how much easier would it be to be able to communicate than by using traditional 2D drawings? Let's see what Chris has in store for us on this.
Thanks, Scott. If you have the desire to go more paperless, we may have the answer for you. Our NX Technical Data Package application has the power to package up 3D viewing data, 2D drawings, shop floor instructions, and a wide variety of other documentation, all in a convenient 3D PDF file. Imagine the power of being able to view PDF files right on the shop floor. Let's take a look at what I mean. As we review the list of members, notice how each member is its own component. While this method lets you design quickly, manufacturing will want a consolidated group of identical members. That way, they can save machine setup time. A member consolidation operation finds geometrically identical members and creates a single component. A review of the results shows how identical members were consolidated into a single component. If any last-minute changes are needed, make an edit and repeat the process. For example, let's add some mounting holes to the member that was part of the consolidated group. Here, we'll enter modeling and punch a few holes in the upper flange.
So we can focus on the consolidation process, we'll skip the process of placing holes in an exact location. Once the holes are placed, it's a matter of rerunning the consolidation process. The consolidation operation looks for geometrically identical parts, and if a part is, say, mirrored, the system is smart enough to consider them different. Because of the newly added holes, this member is no longer geometrically equivalent to its counterpart. Watch as the process removes this component and places it in its own group. A quick selection of the members shows it's now a unique component. Now we're ready to create drawings. NX supports traditional drawings with automatic view creation, dimensions, and parts list. However, let's see if we can't expedite that process. We'll add PMI dimensions directly on the model and create a 3D PDF document. We'll start with ordinate dimensions on the left view. We'll only need to add overall and location dimensions since the parts will have been cut to length. PMI in NX is smart enough to associate these dimensions with the correct view plane. Then later during viewing, recalling that view shows these dimensions. We'll repeat this process for the front and top views. Adding overall dimensions will give the shop floor the right level of detail needed to weld the frame, but not take a lot of time to add. It's important to note that a wide variety of annotations and dimensions can be placed directly on the 3D model. You can add linear, radial, angle, and hole callouts. Geometric tolerancing can also be included, such as datums and feature control frames, as well as surface finish symbols. Have a look at the rich command set on the main toolbar. You can also add weld symbols, but since those were automatically added during the weld definition process, we get those for free. In about a minute, we detail the top, front, and side view. Now we can publish everything in a convenient drawing package. We'll pick a custom template, add the project number and customer name. We can also include special engineering documents such as shop orders and notes. Once complete, NX Technical Data Package creates a 3D PDF complete with drawing views, parts list, and other information the shop floor needs. As we review the PDF, notice the rich content: model views, parts list, and even a table of dimensions. If you need to inspect inside the model, cutting views can be created right inside the PDF document. Cut in the X, Y, or Z direction and other options can enhance the viewing experience. Other types of inspections can be done by adding dimensions between geometric parts. Here, we'll add a dimension to double-check the member's length. Selecting any of the dimensions in the PMI table, highlight the dimensions in the model. And a handy zoom option lets you zero in on the dimension for precise inspection. This capability will help the end user verify key manufacturing steps. Notice how the parts list includes cut length and end cut details. Watch as we highlight members in the parts list and the associated component in the view becomes emphasized. This can help ensure the welders are assembling the correct components. Before we sign off the document, let's have a quick look at the shop order. Remember, we attached this document to the original technical package, but recalling it is easy as opening the document. All looks good, so let's approve and date the technical document. Then we can print, save, or email the job package.
Wow, Chris, another home run on that one. Now we have a lot less time that's needed to complete the documentation set. And how do we accomplish that? We accomplish that by using all the information we collected throughout the entire design process and then just automatically putting it into our technical data package template with minimal input from the end users to be able to create that documentation package. NX is a scalable solution where applications from mechanical, electrical, automation, and process are all connected together in one easy-to-use platform. The bulk of today's area with frame design was spent in the product design area of NX. But as you can see with product design, we have shown you that being able to build frames is very easy and very quick using NX. Also, if you look at the other areas of NX, there may be other areas of interest to you down the road. NX is the most complete solution available today that helps you break down the barriers to innovation and get the best solutions possible with the shortest amount of time without having the need to re-edit and remaster data in multiple systems. NX is the complete solution for all your engineering needs.
Frame design can be just that, a complete solution from design, finding interferences between moving parts, structural simulations, automating the welding documentation process, or packaging everything up in a convenient-to-use 3D PDF file. All these applications have flexible licensing options. You can either own the software permanently or purchase it on a subscription for periodic use. But my personal favorite are tokens. Purchase tokens and use any application that you want. We started this webinar off with a simple question. Let me rephrase that. Based on what you just saw, what area do you think will help you become more productive? The design aspects for frames, finding interferences between moving parts, structural simulations, the welding documentation process, or viewing with 3D PDF files. Again, I'm Chris Kasperzak, and thank you for watching.
We hope you have enjoyed today's session on frame design made easy. And always remember that NX makes it real.